Okay, so today I am talking about the derivation for degeneracy pressure in a completely what? Degenerate gas, but this is non-relativistic. Okay, this is not relativistic case. This is basically non-relativistic case. Now, regarding white dwarf, you will remember that we have already done this derivation previously, but today what I would like to show you the same derivation for degeneracy pressure using very basic ideas of uncertainty principle. So the first step was finding the average separation in a gas having volume V and total number of particles N. So what will it be? So if we have a gas of volume V and total number of particles N, then the volume or then the number of number of particles per unit volume will be what? Inverse of this, N by V, right? And similarly, that will be equal to lambda S cube, that is the average separation cube, and by this way we will be able to find the average separation. So here we are considering completely degenerate non-relativistic electron gas. Completely degenerate, number one, non-relativistic electron gas. Three things. T is equal to 0 case. Finite temperature case I am not talking over here. Okay, so this is the first thing. Next, what we did was we invoked the uncertainty principle, right? So if the electrons, they need to have, because they will follow the Pauli's exclusion principle, and we are talking about white dwarf, completely degenerate case. So they will be compressed, but this compression means that Pauli's exclusion principle will be satisfied. That means the average separation, it cannot be lower than this thing, right? So if I estimate the uncertainty in position, it will be roughly of this order. Let us try to make an estimate. So the uncertainty in position delta x will be of the order of this average separation. Next, again we are invoking the uncertainty principle and we are trying to find the momentum. So momentum is of the order of delta p, and then we found the momentum in this case. After that, till now what we have done? First we have found the average separation. Next we invoked uncertainty principle 2 and 3. After that we are now talking about the non-relativistic case. Now when I am talking about non-relativistic case, then how we write it down mathematically? We will just write P is equal to mv, and if it is a relativistic case, we will just write V is equal to C. That's it, nothing else. So non-relativistic case, V is equal to P by ME, and so we will get the similar expression like that. Now after this, so up to this part we have got V, we have got P. Fine. Now what is our aim? Our aim is to find the pressure, and in this case we will be guided by the pressure integral. This is a very important theorem, right? This is the general theorem. Now if you do the full calculation, if you input all these things over here and you do the full calculation, you will get this result. However, to make matters simple, if we assume here that all the electrons have same momentum, then this will be very simply reduced to this form, and here you will get a very nice and simplified expression. So I have written here both these expressions. This is for full calculation. Try to do this at home and then give me your feedback, right? And this is the simplified version. Okay. Now the most important thing about this result is, you will see, forget about these constants. Okay. What's the most important thing over here? The most important thing is pressure proportional to rho to the power 5 by 3. This is the most important thing over here, and there is no temperature dependence. Remember, I have been repeatedly saying these things, that quantum gas here, or completely degenerate case, compared to ideal gas, is very much different in several ways. One of the ways is the temperature dependent. right? And remember, it is this pressure which is responsible for hydrostatic equilibrium in white dwarfs. In normal star, it is the basic gas pressure. We have already derived those, right? But here it is this case. Now you might be wondering, sir, in the white dwarf we also have others, atoms also, ions also. So what's the pressure? The pressure will be the same that we have calculated. But if you find out the value, you will see that this value is much higher compared to the gas pressure. And so since it is higher, this is the one which is responsible for going against the gravity, right? So now previously it was just your gas pressure, now it is degeneracy pressure plus gas pressure, but this degeneracy pressure is much larger than gas pressure. So we are not talking about gas pressure anymore, since this is much more important here. It is the one which is really responsible for maintaining the hydrostatic equilibrium. That means P is equal to the pressure due to the gravitational force, right? So that's it. So remember, don't forget that here the gas pressure is absent. No, it is not absent. You can just calculate it. But we are not doing this over here because we have already discussed this for a normal star. But this was absent in the normal star, and this is present in a white dwarf star. And this is much more larger in magnitude. And that's why this is the one which is deciding the physics over here. Okay. Okay, so after finding the degeneracy pressure, let me now find the central pressure in a white dwarf whose mass is mWd and radius is rWd. And this is very simple. We have done similar calculations a lot of time. So again we are going to use the hydrostatic equilibrium and simplest case possible, constant density case. So this is how it is done. So I have written mass like this, and then I am getting this expression. So while doing this integration, the boundary condition will be pressure at the surface equal to 0, which is this, and finally I get this expression. Now we are talking about central pressure, that means R, P and R equal to 0. So this is the expression. This is the central pressure. So next what we will do is we will equate these two terms and try to find the expression for radius. Try this, find it. Check what you get. Equate these two expressions and see what you get. Okay, so we have got degeneracy pressure expression over here. We just derived the central pressure expression over here. Now another one is the constant density. So if I use these three expressions, as I just told you, you will get this relationship, or I asked you to use these three expressions and find an expression for R, radius of the white dwarf, and this is what you get. Now what do we get from this relation? If you forget the constants over here, then this is the one which is most important. So what you get, you see, is the following: mass of white dwarf into R cube is equal to constant. Now what's the entire volume? 4 by 3 pi R cube. So basically this means mass into volume is equal to constant, or density is proportional to mass square. What does this mean? This means that the more the massive white dwarf, suppose we have got a helium white dwarf and another carbon white dwarf, right? Which one is more massive? Carbon white dwarf, right? Now the carbon white dwarf has got larger ends, and so it will be having lower V, lower volume. So this means that more massive white dwarfs are in fact not larger, they are in fact much more smaller. And the reason is what? Because if the white dwarf is more massive, then we need more degeneracy pressure, right, to have hydrostatic equilibrium. And that degeneracy pressure we can have that only through having very high density. Look over here. Very high degeneracy pressure requires very high density, and so electrons need to be squeezed, and this way we will be able to generate the required degeneracy pressure so that we can have hydrostatic equilibrium in white dwarf. So this is the mass radius or mass volume relation. Okay. Now next we will talk about Chandrasekhar mass limit from this case. Okay, so this is the same old mass radius relationship that we obtained previously, right? Where we found mass into volume is equal to constant. Okay, good. Now you see from this relation, let's do some sort of limits. So suppose if we keep on increasing the mass, that means if we keep on adding mass to the white dwarf, what will happen to the radius? See, if we keep on increasing the mass, the radius will tend to 0, or the density will become sort of infinite. But is it really possible that density can become infinite? No. These are just mathematical stuff. The real world is different. So, the first step is this. As soon as the density will reach 10 to the power 6 gram per centimeter cube, what you will observe is deviation from this relationship. And what does this mean? Why is there deviation from this mass radius relationship? This is because till now we are considering a white dwarf completely degenerate case, t equal to 0, completely degenerate case, non-relativistic case. But as soon as density keeps on increasing because of our increasing mass, more and more stacking of mass, density keeps on increasing, what will happen is the velocity of the electrons keep on increasing, and slowly the electrons, few of them will start becoming relativistic. Okay, now things change. How things change? Let me show it to you mathematically, how things change. Okay, so again, previously we talked about the non-relativistic case. Now let me talk about the relativistic case. So this is the expression for the relativistic case, degeneracy pressure. Now it can be done in the similar way as we did previously, right? Using the pressure integral expression and putting V is equal to C over there. And this is the result. The most important thing is this power. Now it is 4 by 3. Previously it was 5 by 3 for the case of non-relativistic case. Now you will see that this simple change of 4 by 3 has dramatic effect. Let's see. So again we will punch these 3 expressions. Number 1, this relativistic case, degeneracy pressure. Number 2, the constant density expression, and number 3, the central pressure. These two remain unchanged. Now if we put it together, you will see that the mass becomes independent of the radius. Previously we have got a very beautiful mass radius relationship, but now we will get a simple expression for mass and there will be no radius involved. What is the meaning of this? The meaning of this is very simple. Previously, if this is an axis with mass of white dwarf increasing, previously, what is the lowest mass of a white dwarf possible? A helium white dwarf, right? This is the lowest. Now, as we keep on increasing, the electrons were mostly non-relativistic in this entire region. Now, as we keep on increasing the mass of the white dwarf, what will happen? We just saw, right? The density keeps on increasing, the velocity keeps on increasing, and slowly they will become relativistic. That means here V will become C. And where will this happen? So if this is my white dwarf, previously this entire region was non-relativistic. But if I keep on adding mass to it, then what will happen is that slowly the electrons will start become relativistic. Now tell me, where will the relativistic electrons appear? In the core or in the outside? Obviously in the core. So you will have relativistic electrons over here, and here you will have mixture of both relativistic and non-relativistic, and all the non-relativistic electrons will be in the outer region. So here we will have relativistic electrons, here non-relativistic plus relativistic, and here we have all non-relativistic. And this is basically the structure of a relativistic star. Right now I am talking about white dwarf. Okay, a relativistic white dwarf. How does it look like? The overall structure. Inside, relativistic electrons, in the middle zone, non-relativistic plus relativistic, outside non-relativistic. Fine. So what, sir, what's the problem? The problem is this: the moment we have got a relativistic case, see, the pressure, power, dependence on density is 4/3, and as a result, n becomes independent of r. This means there is only one mass. Only one mass. And what is this? Which mass is this? This is the maximum mass of the white dwarf. If we exceed this mass, the degenerate core which was there, it will start to collapse. Why? Because now the maximum pressure degeneracy is unable to resist the gravity. Okay. So this is the maximum mass of a white dwarf, and this is the Chandrasekhar limit. And what is this mass? This mass is, if you do this calculation, you will get this result. So Chandrasekhar mass. And we have done a very basic calculation. More, and the result is 0.44 solar masses. If you do more exact calculations, you will get of the order of 1.4 solar masses. But overall, this is a very basic and interesting way to get to the idea of Chandrasekhar limit. Okay? Any questions, any doubt regarding this? Remember, every structure, the star for example, what is the lowest mass possible? When we have hydrogen fusion, that's the lowest mass. What is the highest mass possible? When the photon or radiation pressure is so large that the star just blows away. That's the maximum mass, around 250 solar masses or so. So we cannot have a star with, if I ask you in the examination, can we have a star whose mass is 740 solar masses? Explain. Then you will have to say, what? 740 solar masses, good. What will be the radiation pressure? You calculate it and you see whether it matches with the gravitational pressure. You will see the gravitational pressure and radiation pressure is much larger. It will just erupt. Only if they match can we have hydrostatic equilibrium, can we have a star. So similarly, in this case now, the lowest mass of white dwarf is when we have a helium white dwarf, and the maximum mass is when the electrons start becoming relativistic, and then we have this dependence, and as a result there is only one single mass. That's the maximum mass, Chandrasekhar mass. Okay. Now the same thing will happen again, where in the case of neutron star. So till now we have a star, hydrostatic equilibrium. After that we have got degeneracy pressure due to electrons, and if the mass of the core, degenerate core, exceeds that of the Chandrasekhar mass, it will still collapse. And next we will have neutrons, right? And then the neutron degeneracy pressure will work against the gravity, and then again we will have a hydrostatic equilibrium. So 3 stages, 1, 2, 3. And after neutron there is nothing, so immediately black hole. So there are 3 stops, and these stops will be seen by very massive stars, not by the lower mass stars. Okay. Another very interesting thing, we talked about the mass radius relationship, right? Mass into volume of white dwarf is equal to constant. Now this relation is valid in this non-relativistic range. Again, non-relativistic range. Now as it approaches this Chandrasekhar mass or the maximum mass, you will start observing deviations from it, because slowly the electrons reach the relativistic velocity. Now the thing is that you have also seen in graduation classes also, you just don't approach C abruptly. It takes a very large V, I mean. It will not be just V is equal to C. It will be V is equal to 0.000999, 0.9955, then 0.99556 slowly. And so, in this case, as it approaches, you will start seeing observing deviations in this case. And the moment you start observing deviation, you will start understanding the fact that, okay, now we are moving away from the non-relativistic regime. Okay, so there are many ways to understand it. Number one, now do you remember when I talked about virial theorem? Virial theorem for a non-relativistic case, virial theorem for a relativistic gas. What was it? Stability of a star, non-relativistic, it was there. Stability of a star for relativistic case, it was not there. If you just put a chalk in it, it will just explode. Same thing over here. You see, the moment, the same old thing. We have observed similar thing in the case of virial theorem also. Same thing. The moment it starts becoming relativistic, the electrons now are unable to, at that very high density, they are unable to, what? They are squeezed so much that if you squeeze it more, they will not be able to resist the gravity. And mathematically, you are getting the same old stuff in this way, that there is a maximum mass beyond which the electrons will not be able to withstand gravity. So, if we add a little bit, one more, very small piece of matter to it, it will just collapse. The whole stuff will collapse.